Let us move to the today's class. Today we are going to see about ideal and practical sources. Energy or power source in a circuit. So yesterday we have seen about electric circuit elements. The basic elements are resistor, capacitor and inductor. Okay. By connecting these elements, we cannot do anything because we need to power the elements. Okay. If you power the elements only, the elements will start to work. Okay. So to power the elements, we need a power source or energy source which is to be present in the circuit. Okay. In a DC circuit or a DC toys, the power which is given to the toy is in the form of a battery or a cell. Okay, so this battery is known as a voltage source. Okay, there are two different types of sources. I will tell you. Energy source may be classified into two types. One is a voltage source and the another one is the current source. Okay, first one is voltage source and another one is current source. Ideal voltage source is defined as energy source whose terminal voltage V does not depends upon current I. Okay, you can see this is a battery source and this battery voltage is 1.5 volt. Okay, and this battery voltage will not depends upon the current which is flowing through the circuit. Okay, if a this battery is connected to a resistance of 8 ohm and the current flowing through the resistance and through the battery is I. Current is I. So this current I will not change irrespective of changing the 8 ohm resistors. If you are connecting a 9 ohm resistor, the battery current will be constant, which is I. If you connect a 10 kilo ohm resistance, then the battery current is also a constant, which is I. Okay, so it is known as an ideal source. Okay, the ideal voltage source has a terminal voltage V which does not change and does not depends upon the current source, and the voltage source will also does not change. Okay, can you understand what I am saying? In an ideal voltage source, the voltage 1.5 volt battery will supply a current through the 8 ohm resistance, and the voltage across the battery and the terminal voltage will represented as 1.5 volt will not change. It means voltage of the source is independent of the load resistance RL. So I have already said the voltage Vin of the battery is independent of the load resistance. Okay, what I said to you is written back in the PPT. Any value of load resistance from 0 to infinity, terminal voltage across the source is a constant. Okay, so the load resistance may change from 0 ohms to infinite ohms. So by changing the load resistance, the terminal voltage of the battery will be a constant. And here you can see the ideal characteristics of a voltage source, and here you can see the straight line. This is the current in y-axis and voltage in x-axis. Okay, if we plot this characteristics, you can see the voltage and the current is always, the voltage is a constant. In x-axis, we will start from 0, 1 volt, 2 volt, 3 volt, 4 volt, and similarly it will go to till the end. Okay, if you say this point is 1.5 volt, at any point of this, the voltage will remain at 1.5 volt irrespectivity of the current. You can see the current may change upwards. If you go up, the current will have 1 ampere. If you go further up, the current will have 2 ampere, but the voltage is always 1.5 volt. Okay, this is the characteristics of the ideal voltage source. Okay, and these are the symbols of the voltage source. Here you can see this is the AC voltage source and a DC voltage source and a battery voltage source. and these are the symbols of the voltage sources. If we use a direct current, then we can use the symbol of plus minus, or like a plus or minus symbol as a battery. Okay, if we use a alternating voltage current, then we need to use the sine waveform instead of plus or minus over here. The next one is the practical voltage source. In the previous slide, we have seen about the ideal voltage source, and this ideal voltage source has a constant voltage irrespective of the resistance connected with it. Okay, but in a practical case, in the real case, okay, in a real scenario, it will not be like that. Consider a load resistance is connected to a practical voltage source, say battery. Okay, you can see this is a battery which is connected to the load resistance RL. Say this is the battery. Okay, this complete setup which is in dashed line is the battery. Okay, this battery is connected to the load resistance RL. When resistance RL across source is decreased, then load current I gets increased. As a result, the practical voltage across the source terminal get decreased. Okay, if you decreases the load resistance, okay, say the value of this voltage source is 10 volt, okay, and the value of this resistance is 10 ohm, okay, then we need to find the current which is flowing over here. Okay, how we can find this current? We know V is equal to I into R, then I is equal to V by R. Okay, now we can substitute V is equal to 10 volt and R is equal to 10 ohm, and you can get a value of 1 amperes of current is flowing over here. Okay, 1 ampere of current is flowing over here. Now let us change. Now here the 10 ohm resistance is decreased to 5 ohms resistance. Okay, now let us calculate back. Now we can get 10, which is the voltage source V, and R is now decreased to 5 ohms, 5, and now we can get ampere of 2 amps. Okay, if the resistance in the RL changes, then the current flowing through the resistance gets changes. Is it true? Is it true? You can see when you give a 10 ohm resistance and the battery voltage is constant, we have fixed the battery voltage as 10 volt, but if the resistance changes from 10 ohms to 5 ohms, for 10 ohms we will get a current of 1 ampere, and for 5 ohms we are having a current of 2 ampere. So this is the practical scenario that the ideal source will fail because the ideal battery will fail. There is nothing ideal in this world. So the ideal represent is only used for study purposes. But in practical cases, the ideal sources will fail and the current will change, starts to change. Okay, so by changing this current, so the battery starts to discharge faster and decreases its voltage level. So a very simple example is if you buy a battery, new battery for your remote control, your remote will work very fine. After a few months, what will happen? The battery will drain and loses its voltage. Yes, then your remote control will not work back. So you need to replace the battery back. Why this happens? Because the current present, that is the charge present inside the battery, is eliminated as a current, and this current will drain the voltage source, and the voltage source will get from 10 volt. After a long period of time, this 10 volt will drop down to 1 volt. Okay, so in a practical voltage source, the changing of resistance will changes the current flow, and this current flow will decreases the battery voltage day by day. Can you understand? Okay. In this graph, so convert a practical voltage source into ideal voltage source. A source resistance RSV is modeled inside the source itself and known as source resistance. So, in the real scenario, we have seen the practical voltage source is a very different from an ideal voltage source. So, to make this alternatives to be equal, so what we are going to make is we are going to add a source resistance which is RSV. Okay, this RSV is connected inside the battery, and this RSV is not seen physically. If you buy a battery, can you find a resistance inside a battery? Is it present in? No, it is not present in. But the battery itself has a resistance RSV present in it. Okay, you can see there is no physical existence of point C inside the source and it is not accessible. See, this is the battery and this is the source resistance RSV, and there is a point C over here, and this point C is not present, but it is an assumption. Okay, it is not accessible because this RSV, that is the load resistance or the source resistance, is used to match the ideal voltage source and a practical voltage source. The ideal resistance is included to account for the non-identity of the practical voltage source. So we have seen ideal voltage source which has the ideal voltage for all resistance values, but in practical cases it is not such a that. So to make the accountability easier, we are adding or we are assuming that a resistance, that is a load resistance, is present inside a voltage source, and we are modeling this complete setup as a battery. So only we are drawing a dashed line for a battery plus the load resistance. Okay, the linear relationship between voltage and the current is given by VL, that is the load voltage, which is represented over here. VL is equal to VSV minus RSV into IL. Okay, this is the load voltage VL, and the VSV represents the this voltage, the voltage drop across the, sorry, this VSV represents the voltage across the battery over here from the C point to this point. Okay, and this RSV into IL represents the voltage drop across this point. Okay, this represents RSV into IL, and from this point to this point you have VSV. Okay, so the total load voltage VL can be VSV minus RSV into IL. The open circuit voltage, that is VLOC, will be equal to Vs, because if the load resistance is removed, if you will remove this load resistance, then this source resistance has a no point of effect. So if a source load resistance is present, then only the source resistance will be present. If the load resistance is removed and it is measured, then the open circuit voltage, that is the VLOC, will be equal to the supply voltage, that is the battery voltage Vs. So I will tell you a small example. Okay, if you are buying a new battery and measuring it in a multimeter. Okay, if you are having a multimeter or a voltmeter, then you are buying a new battery and measuring in a multimeter, it will show you 1.5 volt accurately because it is a new battery. And if you are putting it in a remote control and you are using for several years, okay, after that your remote control has failed, you are going to replace the battery. Okay, if you remove the battery back and measure it back in the multimeter, it will show you 1.5 volt. Why it does? Why it's showing the correct value back as the new value? Because the load is removed. If you put the same battery again into the remote control and measure as it is in the remote control, it will show you 0 volt, because the load is connected to the battery. The remote control is connected to the battery and the battery has to supply power to the remote control. And at this time, if you measure the battery voltage, the battery cannot give you power to the remote control as well as to the multimeter to charge it. So when it is working within the remote control, the battery will show you a 0 volt. And when you take the battery out and measure it back, it will show you some voltage of 0.8 volt to 1 volt or sometimes 1.5 volt. It will show some other values. Okay. Okay, this is the characteristics graph of the practical voltage source, and here is the BL, which is the no load voltage, that is the complete voltage from A to B, and this is the load current IL, and we see the ideal source in the dashed line. So in ideal source, the voltage will never get decreased. If it is a 10 volt battery, it will be 10 volt battery for always. Okay, it will be 10 volt for always. But there is no such batteries available. So in a practical source, you can see the voltage starts to decrease when you starts to use. Okay, if you connected the 10 volt battery to a remote control or some other appliances, it will start to reduces its voltage and goes to the 0 volt. When it goes to the 0 volt, the remote control will not work. Okay, this is the practical case and this is the ideal case. And next we are going to see about ideal current source. Ideal current source. It is defined as an energy source which delivers constant current I independent of its voltage. Okay, here you can see the difference from a voltage source, that is the ideal voltage source, from a current source is, if it is an ideal voltage source, the voltage will be constant irrespective of current. Okay, in an ideal current source, current will be constant irrespective of voltage. Can you understand? If it is a voltage source, voltage will be constant irrespective of current. Current may change. Okay. In the ideal current source, the current will be constant irrespective of voltage. That is the difference. It means that current through the source is independent of the load resistance RL. So this is the circuit diagram and the symbol of the current source is here. Okay, this is the DC current source and this one represents the AC current source, and another one figure is also here. I did not show you in here. You can refer the notes, PDF notes in the Moodle. Okay, uh, if you use the current source to power the resistance, you can see the current, which is the 5 ampere current, is constant. Okay, but the voltage source may change. Voltage of the current source may change, but the current remains constant. Here in this characteristics graph, you can see the straight line is drawn for the current, not for the voltage. If you take this point as 10 ampere and this line completely will be in 10 ampere, but the voltage may change. Here it may be 0 volt for 10 ampere, 1 volt for 10 ampere, 2 volt for 10 ampere, 3 volt for 10 amperes, but the ampere rating remains the same, whereas the voltage starts to change. Any value of load resistance from 0 to infinity, current through the source is a constant. Okay. So if the load resistance connected over here may change, it may be 10 ohms or 100 ohms or 11 ohms. Okay, it may change, but the current which is flowing through the current source and through the resistance will be 5 amperes, but it will not change. Practical current source. We all know in practical cases that it will not be like that. Okay. A practical current source is modeled as an ideal current source by adding parallel resistance across the current source. Okay. For a for a voltage source, what we have done for a voltage source, for a practical voltage source, we have added the resistance in series. This is the voltage source. We have added the resistance in series. Okay. But But for a practical current source, we are adding a resistance in parallel. Okay, this is the difference. Okay, this is the difference in circuit for practical voltage source and current source. For practical current source, we need to add the resistance in parallel with the current source. Whereas in practical voltage source, what we are doing, we are adding the resistance in series with the voltage source. The resistance RSL is called internal resistance or source resistance. This is same. This RSL or RSI or some other RL or Veru RS. This is the same. Okay, this is known as source resistance or internal resistance. In different books, they will give different acronyms. Some will give RL, some will give RS, someone will give RI. Okay, this represents internal resistance or source resistance. The characteristics of a practical current source, whereas IL is equal to IS minus VL divided by RSI. That is the total load current IL. We need to find the total load current IL, and this total load current will be equivalent to the source current IS. This is the main source. Okay, so this source current is the main. So we need to differentiate, that is the subtract the value from IS minus VL divided by RSI. Okay. This is IS. Okay. So this current will go through this and also this. Okay. So when this IS is flowing like this, then we need to find the current, how it flows over here. So to, sorry, I made some small mistake over here. Okay, this current is IS. Okay, and this current, when coming at this point, it will divided into two parts. One part of current will go through this and another part of current will go through this resistance. Okay, so the current which is going out through this path is known as IL. Okay, and this one is the IL. Okay, this IS is the total source current. Okay, we need to find the current which is flowing through this source internal resistance. Okay, to find this, we know V is equal to IR. We all know this formula. Okay, so we can make I is equal to V by R. So the voltage across this resistance, we need to find the voltage across this source resistance, which is nothing but, you can see, this is VL. Okay, this complete voltage is parallel to this resistance. Okay, so the voltage across the source resistance will be VL, and the resistance is what? RSI. Okay, so we can substitute IS minus VL divided by RSI, and we can subtract this value from the source current to find the load current. the open circuit voltage, that is the VLOC, that is if you remove this load RL, if you remove this load over here, okay, if you remove this load, then the open circuit voltage VLOC will be equal to the total drop across RSI into IS. Okay, will be equal to RSI into IS. Okay, then the short circuit current, if you connect the two terminals A and B, okay, if you connect these two terminals A and B in a closed path and short circuit their resistance, what is the current? Then this complete source current IS will be flowing in this path. So the short circuit current ILSC will be equal to the source current IS. Okay. Then in the characteristics graph, you can see for ideal current source, the current will be constant for all the time. Whereas in a practical source, the current will decrease when the voltage starts to increase. Okay, and this characteristic graph is shown over here.